let's look at another volume of a solid revolution example in this video. So I've got the curve y equals e to the minus x. We've got the line y equals 1. We've got the line x equal to 2. So we've got this is the region that we're interested in, bounded by those curves. But rather than rotating it around one of the axes, we're going to rotate it around the line y equals 2, which would be up here. Okay. So to get a visualization of what's going on here, the line y equal to 2 would run right through the middle of this blue cylinder here. It would run through the middle. Okay. So when we rotate this region around the line y equals 2, here's our region here, rotating it around. So this horizontal line here is what's giving us this inner cylinder. And then the curved piece here is what's giving us this pinkish, reddish piece here. And again, there would be a bottom to this, if you will. There would be a piece here that would close it off to give us a volume. But I didn't want to put that in there because you can't see what's going on. All right, so again, we want to figure out what the volume of this thing is. Again, the only real way we have to be able to do this right now is to be able to do this by slicing it perpendicularly to the axis of rotation to give us either a disk or a washer. So going perpendicularly would mean we're slicing up our x-axis, which tells us that we're going to integrate with respect to x immediately. It just tells us that immediately we're going to integrate with respect to x. Okay. When we slice this way and rotate, now remember, this is our axis of rotation, the y equals 2. So we're going to get this washer here going around y equal to 2 here. And again, that's going right through the middle of this cylinder. So this bluish, purplish thing here is what that disc, or excuse me, that washer looks like. To find the volume of a washer, we need big radius and small radius. Now again, the radius here is going to go from axis of rotation to the curve. So our axis of rotation here is at 2. To get our big radius, we're going to go 2 minus e to the minus x, because it's going to be the distance from the axis of rotation to the curve. 2 minus e to the minus x. We'll square that radius. The small radius will be 2 to 1. And then we'll square that radius. And again, remember, it's the square of each individual radius and then subtraction, right? It's a difference of squares, not a square of a difference. That's an easy one to mess up. Okay. Remember, we're finding area of a big circle minus area of a small circle and then multiplying by a height. That's how we're getting a volume. When we do an area of a big circle, I've got to square that radius. To do area of a small circle, I've got to do that radius and square it. Okay. So square the individual radii. All right, so if we multiply everything out and simplify, here's what we get for our integrand, e to the minus 2x minus 4e to the minus x plus a 3. Antiderivative here, well, antiderivative for 3 is 3x. That one's pretty straightforward. Here, when I do an antiderivative of e to the minus x, I've got to adjust for the minus that's in the exponent. So instead of having a minus in front, we'll have a plus. Likewise, for this first one, we have to adjust for having a negative 2 in the exponent, so we'll have to divide by it when we do an antiderivative. You could do each of those with a u substitution if you need to, but these are ones that you should be fairly comfortable with just being able to write down their antiderivative by adjusting for the constant that's up in the exponent. And then finally, to finish this off, you'll plug in your upper limit of integration, plug in your lower limit of integration using fundamental theorem of calculus, simplify, and get pi times the quantity, 5 halves plus 2e to the minus 2 minus 1/2 e to the minus 4 is our volume.